Last time we developed the basic wave equation describing the cold fusion deuteron intermediate state. We did this by starting with Feynman's path integral wave equation. And in the Lagrangian describing two deuterons and one electron, we expanded the deuteron-electron potential around the z-axis with x and y equals 0, with the z-axis always passing through the two deuterons. We keep only the second order term giving a parabolic potential in x and y. The wave equation was then converted to the differential form except for the electron x and y components, which are left in the path integral form, which we will deal with later. In this video, we developed the electron wave function along the z-axis using the Schrödinger equation. We use the same Born-Oppenheimer approximation used with the hydrogen molecule analysis. This works only for the z component, as the deuterons do not move enough in the radial dimensions during the electron time constant to matter. So we need to solve for the electron wave function and energy as a function of the deuteron separation. This is completely analogous to the hydrogen molecule analysis. We will find that the electron passes through the nuclei and has a significant probability in and near the deuteron. So unlike the hydrogen molecule, we need to describe the Coulomb potential in the nuclei, which requires knowing the charge distribution. Also, because of the high probability in and near the nuclei, the relativistic mass increase of the electron must be accounted for. We start by describing the two nucleons in a deuteron with a quantum model using a square well nuclear potential. The proton radial probability distribution is then just the square of the wave function. We use the same assumptions successfully used in density function theory, where the energy is calculated from the probability distribution of the particles. The difference being the energy is negative, i.e. attractive, instead of the repulsive positive energy in density function calculations of electrons. Using Gauss's law, we integrate the probability from 0 to r to get the charge felt by the electron at r. This slide shows the proton wave function times r. This next graph shows the relative charge felt as a function of the radius in the nuclei. The potential for the electron is then simply the Coulomb force with charge as a function of radius integrated from infinity to r. So outside the nuclei, the potential is just the normal Coulomb potential, and inside the nuclei, the potential comes from the integration of the changing charge due to Gauss's law. This slide shows the relative potential calculated in this way compared to the normal 1 over r potential. Note that in the nuclei, the potential is nearly parabolic as required for separating the x, y, and z wave functions. Now we need to adjust the electron mass due to the relativistic velocities in and near the deuterons. We do this using the potential for the electron just calculated, then subtracting the energy that goes into the orthogonal x and y velocities and the energy given up to the deuterons. Any potential left goes to the electron. We assume an electron velocity and mass produced by this potential. Thus, the electron kinetic energy, 1/2 mv squared, is equal to the potential at a given point minus the energy lost, which is the same as the average electron energy E sub E that we will find by solving the electron wave function. The relativistic mass is calculated the normal way with the two equations and unknown mass and velocity. We can calculate the relativistic mass increase along the z-axis. This figure shows the most dramatic relative mass increase of the electron by a factor of 7 in and near the two deuterons when they are only 5 Fermi apart, just before fusion. With the relativistic mass adjustment and the charge distribution in the nuclei giving a complete potential, we can then use a standard differential equation solver, in this case MathCAD 14. We use a conventional shooting technique, as shown, adjusting the electron energy until the boundary conditions are satisfied. A typical wave function is shown for a deuteron separation of 0.1 angstrom. We can then generate a graph of electron energy versus deuteron separation, as shown here. As the deuterons approach within 5 Fermi, the electron energy is about 70,000 electron volts. Next time, we will use this energy separation curve to generate the pseudopotential in order to solve the deuteron wave equation.